So the purpose of this next exercise is to show you that Spark can often be used to parallelize problems that you might not have thought Spark could do. So a lot of times people use Spark for data analytics and specifically for things that can be expressed as a SQL command, but it can do so much more if you just think creatively about it. So as an example, let's figure out the degrees of separation between the superheroes in our superhero social network here. To recap what the idea of degrees of separation is if you're not familiar with it, well, back in Hollywood, there used to be a concept called your Bacon number. And that was how many degrees of separation an actor was from Kevin Bacon. There was this legend that Kevin Bacon was so well connected and appeared in so many different movies that almost every actor could trace themselves back to Kevin Bacon somehow. And it's true, actually. So how does that work? Let's put that in terms of our superhero data, right? So let's say that for the sake of argument, Spider-Man appeared in the same comic book as the Incredible Hulk. And the Incredible Hulk, in turn, appeared in the same comic book as Thor. In that case, we would say that Spider-Man and Thor are 2 degrees of separation, right? Because if you look at Spider-Man's connections, the Hulk isn't in that immediate set of connections, but somebody that Spider-Man connected to is connected to the Hulk. So that's 2 steps away from Spider-Man, or 2 degrees of separation. So that's an interesting thing to look at. It turns out that people are closer connected than you might think. And it turns out that's also true in the world of comic books. So how would we do this? Well, there's a computer science algorithm called breadth first search that solves this kind of problem for us. And this certainly isn't something where you would just write a SQL command and be done with it to find the answer, right? We want to figure out for any given person, any given node, in this case, any given superhero, in this graph of connections, how many steps away is a given superhero from any other superhero. So how would we do this using Apache Spark? Well, before we talk about the implementation details, let's talk about the algorithm. So to understand this example, you need to understand breadth first search, or BFS. This is a computer science algorithms problem, and if you are going to be interviewing for software engineer positions, it's a good thing to know, although it's not directly related to Spark. So if you don't follow the details here, don't get too hung up on it. It's not really relevant to Spark itself. It's just relevant for understanding this example of how Spark can be used to solve problems that you might not have thought Spark could be used for. So imagine this represents our network. So every circle here represents a superhero, and every line between those circles represents a connection between superheroes. So that means that they appeared in the same comic book together. And sometimes you have many connections coming off of a superhero, and sometimes there are many routes between 2 superheroes to look at. So the number inside each circle represents the distance of that superhero from whatever superhero we're measuring the degrees of separation from. And initially, we don't know the answer as we're starting this algorithm. So everything is set to infinity. We assume that they're infinitely far away because we haven't computed it yet. So to start, we pick the superhero that we want to start with and who we want to compute the degrees of separation from. So let's say that's Spider-Man, and we'll call that S here in this example. So to kick off the algorithm, we color that initial node gray, meaning that we need to explore that node. We want to find out more about the connections from that node. And we put in the number 0 because that's the distance from the person we're starting with to that node. Spider-Man is 0 degrees of separation from Spider-Man because Spider-Man is Spider-Man. So what we do in the BFS algorithm is that we go looking for gray nodes in our graph. And for every gray node we find, we explore the connections coming off of that gray node. And when we do, if that node that we're exploring is white, meaning that it has been unexplored previously, we will color it gray, meaning that we need to explore that node further iteratively. And we'll take the node that we just explored and color it black, indicating that we've already explored that node. We don't need to come back to it again. We increment the current count of distance, so 0 plus 1 is 1. So now we know that we're 1 degree of separation on R and W. Makes sense? So we started exploring that initially gray node S, colored it black because we're done with it, and for all of its connections, if they were white, we make them gray now and put in the current count of distance from that initial node. So in the next pass, again, we look for the gray nodes and explore their connections. So let's start with W there. We'll break out its connections. So those were both white originally, and now we're going to color them gray and increment the distance again. So now we're 2 degrees of separation from S. We'll do the same thing for the connection from S to R. Explore its one connection to V and color it gray, and again put a 2 in there because we're currently at the iteration of 2 distance from S. Now that we've explored R and W, we're going to color those black, meaning that we should not revisit those again in the future. Next, we'll start with T. Again, we need to go through all the gray nodes and explore their connections again. Now T is connected to U, which was white, so we'll now color that gray and increment the distance count again to 3 now. Now note that T is also connected to X and W, but those are not white. We're going to try to preserve the darkest color here as we go through, so we're not going to bother revisiting X again. It's already marked gray. We're definitely not going to visit W again because that's marked black. That means that we've already done that one. We don't need to process that one at all. So we can mark X as being explored now. We can mark that black now because we've already determined that we're done with it. And moving on, we also need to explore R. We haven't finished that one yet, so we'll go and check off V as being black now as well. That was gray originally, so now the next step is to just call that black, meaning that we're done exploring it. Now we just have 2 more gray nodes to explore here, and they don't have any newly unexplored nodes associated with them, so we're just going to color them black and be done with it. So the overall algorithm here, to recap, we start off by coloring everything white with an unknown distance. Our initial node is gray, and for each iteration, we look for gray nodes, explore their connections, and for every white node coming off that gray node, we will mark it as gray for future exploration, unless it's already been colored gray or black. We're basically preserving the darkest color there as we go. And furthermore, we are preserving the lowest distance metric that we see in these nodes as we go. So we're never going to do something like go from U back to T and say that T is now a distance of 4 because we backtracked. That wouldn't make sense, right? So we would always preserve that lower distance metric as we're traversing the graph. So it is kind of a hard thing to wrap your head around. And again, if you didn't quite follow that, don't worry about it too much. This is not a course about algorithms. It's a course about Spark. I'm just trying to convey how it's possible to use Spark to solve problems that maybe you wouldn't think Spark was suited for. You can actually parallelize this problem pretty well if we think about it in a creative way. So let's talk about that implementation in Spark next and make this happen on our Spark cluster.